Hey all, my name is Alex Hall and I'd like to welcome you to this presentation about the FireHashJoin. This is a novel implementation of the so-called HashJoin algorithm, its main aim being to have a low memory footprint. This has been joint work with Leonard and other colleagues here at Firebolt. Let me start with a quick outline of the presentation. I'll begin with a toy example, a simple join query. With that, we'll explain some background of the just standard HashJoin algorithm. I'll then go into the motivation of why we actually built the FireHashJoin in the first place and tell you a bit about like the concepts that we took and that we looked into. And finally, I'll close with some stats of the impact in prod of this new implementation on essentially query performance and memory usage. All right, let's dive in. Our toy example is based on two tables. On the left side, you see a fact table, which has only one column, and in this case, actually only one row. On the right side, you see a dimension table dim, which has 10 million rows and 2 columns. So if you will, the fact table is somewhat degenerate, but this is a toy example anyhow, so it doesn't really matter. If you like, you can imagine it stemming from some very restrictive where statement or so. Anyhow, this is the query. This is the query that we'd like to compute. It's essentially we're joining on A equals to B, and we want to select A and C from these two tables. So essentially, since we have only one row on the fact side, we're looking for a row on the dimension side, which has the value 5 million for column B. And then the result will be if columns A and C of these rows. So essentially, the result that you see below is the tuple 5 million, 42. All right, that's our simple example. So how do we actually compute this? Well, here we use, as we mentioned, the HashJoin algorithm, and this is very, it's well known. It's been proposed in the late 1970s, and it's actually the most commonly used algorithm in analytical DBs. It comprises of two phases. The first phase, in the build phase, we actually build a hash table for the dimension table, so the large table on the right, and in the probe phase, we use that hash table and we go over each row in the fact table, in our case only one. We go over each row of that and then probe the hash table for that. So let's look in more detail at the build phase. So essentially what we're building here is a so-called chaining hash table. That's just one way one could implement it. In order to build it, we go over the dim data set row by row and then build up this table on the right. In the middle, you see conceptually what we're building up. We're basically coming up with a map from column B to column C. So let's start. Let's say we go to row 1. We want to map key 1 to value 47. Conceptually, how do we do that in more detail? We compute a so-called hash bucket, and for that value of 1, this would be hash bucket 1001, and into this bucket, we add the tuple 1, 47. Then we continue to the second row. Here we want to map key 2 to value 11. So we compute the hash bucket. That would be this bucket, the new bucket that you see below, and we add that tuple 2, 11 to that bucket, and so on. We finally reach, say, the key 5 million and the value 42. Now, what happens here is, as you see, we get the same hash bucket that we had before, 1001. And since we already have an entry in that bucket, what we do is we simply append this new entry, the tuple 5,042. We just append it to the end. And then we continue through the whole table, and in the end, we have built our complete hash table, if you will, on the right-hand side. Okay, how do we use it in the probe phase? As mentioned, we go over this fact table row by row and probe the hash table. So on the left, you have the fact table with only this one row, 5 million. So conceptually, we want to look up for the key 5 million. We want to look up its value, 42, and that would give us the result. In the bottom, how do we do this in details? With the data structure that we just built up. So we compute, again, the hash bucket of 5 million, which is this 1001 bucket that we've seen before. Then we go over the entries in that bucket. We start by the first entry and compare the keys. We see that key is key 1. This is not equal to 5 million, so that's not what we're looking for. But the second one is actually for the key 5 million. So we found the tuple that we were looking for, and we returned 42 as the value that we're interested in. So and that's basically beginning to end of how we, at a high level, would compute a hash join for this specific query and this specific data set. All right, with that, let me switch to telling you about the motivation. So why did we build the FireHashJoin? Well, as I mentioned, The main aim was really to have a low memory footprint. So we wanted a compact memory layout. So this is just good in general for resource usage, in our case, RAM usage. It's good for CPU caches. So if the more fits into these CPU caches, L1, L2, L3 caches, the faster the query will be processed. We were also, as a secondary goal, looking to have a very efficient and fast multi-threaded build phase where the threads wouldn't step on each other's toes, in a sense, while building that. But again, main goal really to minimize the hash table sizes. Why is that? Essentially, the smaller these hash tables are, the more of these fit into our so-called fire cache. This is an in-memory cache that we have where we store any hash tables that we build. So if a similar query comes later that has the same join, we can just reuse that hash table instead of building it again. So we can, with this fire cache, we can skip the build phase altogether. And obviously, the smaller these tables are, these hash tables, the more we can fit into that cache. So that's the main motivation. So how do we go about it? We had like 3 main building blocks that I'd like to very briefly go over in the next slides, and starting with a compact encoding of tuples. So think of how to present a tuple like 5,000,042. How do we present that in memory? Then the second part is the memory layout of these hash tables. So how do we present these buckets that I've shown you? So say, how do we present bucket 1001 and its pointers to the entries it has? And finally, I'll briefly skim over the multi-threaded build phase and just give you some high-level ideas there. Of course, this is not all that you need to do to build a production-grade join algorithm. There's a lot more. You have all these different join flavors. You need to support arbitrary expressions, so-called theta joins. You need support for nulls, arrays, spilling, disjunctions, and so on. And we'll skip all that in this presentation and really focus only on these basics in the next couple of slides. All right, let's start with the encoding of the tuples. So how do we encode something like 5,000,042 as tuple? Well, we could start and do the fine and very common, what we could call a vanilla encoding, where each of these numbers is encoded as an 8-byte integer. If you know about the concept of little endian and look closely at these 8 blue values that you see here in the slide, then you would see that these are kind of come from left to right. So that's the little endian encoding. And essentially the blue bytes, they're just a hexadecimal representation of the number 5 million. It uses 8 bytes. And then the green values that you see are again 8 bytes in the hexadecimal representation that represent the value 42. So yeah, for these 2 numbers, we would then need 16 bytes. And that's completely fine. In our implementation, which is also fine, that we had before, we have another auxiliary data structure, which essentially we use this vanilla encoding plus that data structure, and then we end up using 28 bytes. So how much do we need in the FireHashJoin? Here we can actually go do by only using 4 bytes. And so why is that? So first of all, we allow ourselves, in a sense, maybe you could call it pretty extreme, we allow ourselves a complete pass over the entire data set to collect some stats. And what we're collecting is really just, for all rows, we find the maximum number of bytes needed for each column to represent it. So here for these 10 million rows, we find out that we only need at most 3 bytes to represent values in column B, and we need exactly 1 byte to represent values in column C. And hence, we can then take these 2 values, and instead of using 16 bytes, we can be 4x smaller and encode them in 4 bytes. So that's already pretty nice. And so what about the memory layout? So this is kind of similar to the picture I've shown you before about this chaining hash table, has a little bit more information, and this would be one way of implementing it. There are tons of other ways, obviously, but one way of implementing it is what you could do is you could use 8-byte pointers to represent the buckets. So each bucket that contains something would have an 8-byte pointer pointing to some location in memory. So say bucket 1001 would point to the location where the tuple 1,47 is stored. And again, 1,47 would be stored in vanilla encoding, just 8-byte integers, followed by another 8-byte pointer pointing to the potential next entry. So in this case, bucket 1001 has a next entry, which is this tuple 5,000,042. And in the last tuple in this bucket, we would just store a null pointer, just 0 in this last entry, so that we know that the chain of such entries is done. So the linked list of these entries is finished. And with this representation, what we end up using in this simple toy example is 830 megabytes of RAM. So now in our new compact hash table representation, what are the basic ideas here? So first of all, the tuples are laid out back to back in a large byte array. So they're all back to back, not spread across memory. Each tuple we use this 4-byte representation that we just discussed in the previous slide. And then also per tuple, we make sure to lay out the values in that tuple back to back in that byte array. So for instance, bucket 1001, it contains 2 tuples, 147 and 5,042. And these would be laid out, as you see here on the right, as essentially 8 bytes, shown in blue and green, which are just come back to back in the byte array. Okay, that's how we encode the tuples. How do we now encode the buckets? So previously we used these 8-byte pointers. Now what we do is we switch over to offsets. So what do we mean by offsets? So let's look at bucket 1001. This line that we have, like this little pointer that we have from that bucket to the right, essentially now is represented by an offset telling us where in this byte array does that bucket start. And then obviously we also need to find the end of that bucket. For that, we just go to the next bucket, 1002. And essentially that end of that gives us the end of the bucket and the beginning of the next bucket. So this is from the offsets how we can figure out where the buckets are in that byte array. And that's good and nice. But how do we now use this to get at a smaller representation? So previously we used 8 bytes per bucket, and now we want to have something smaller. And here what we do is we go to what we call a diff encoding of these bucket offsets. So in short, we store for every 8 entries, so for every 8 buckets, we store a full offset. And for that, we could use like 4 bytes. It's a full offset. And then for the next tuples, or the next buckets, the next 8 buckets, we store 1 byte each to denote the diff. So the length, essentially, if you will, of that entry, of that bucket. And then to compute something like what is the actual offset of bucket 1001, we would look at the corresponding base offset and then would add up to 8 of these little byte diffs. And that's nice and compact. So in the end, on average, we use something like 1.5 bytes per bucket to encode such an offset. On the other hand, of course, as I just mentioned, we do need to compute something to get at the offset. It's not just looking up a single value. But this computation, and I won't go into details here, but this computation, essentially you see kind of a bit of code on the left here, which shows how we can do that computation of adding up to 8 such values quickly in just a few commands. So that's nice, and it turns out to be efficient enough. All right, all good and well. So now we have this compact layout. How do we actually build this efficiently in a multi-threaded manner? I will really skim over the details here and just give you the high-level concept. So we go about this in 3 phases, where we kind of distinguish in how these phases can do parallel work. In the first 2 phases, we do what we call blocks in parallel. So the blocks are essentially the data that comes from our table from below, is sent up as blocks that could have size of 64,000 rows or so. And then the first phase is the stats collection that I just mentioned before, where we compute the maximum number of bytes needed. And here, this obviously we can very easily do in parallel just by going over the blocks in parallel and merging the result in the end. Then again, blocks in parallel, we pre-encode these blocks. So we do this compact tuple encoding now that we know how many bytes we can use per entry. And we compute the hash values. And actually what we do also is we do a hash partitioning. So we sort the entries by their buckets, by their hash buckets. Finally, in the last phase, we now go over the partitioning, and there we go over the parts of that partitioning in parallel. And we reorder all tuples such that, the important thing was that the tuples within a bucket come back to back. So we reorder them such that they have that property, and we compute these compact diff encoded offsets while we're doing so. So summarizing, we're actually doing multiple passes over the data, including we're even sorting the data by hash buckets. So that sounds kind of expensive, but surprisingly, on our toy example, this, for instance, is like about 3 times faster than the previous hash table implementation, really end-to-end, building the hash table. And you can go even further, since this can be done in a multi-threaded manner and the previous implementation couldn't. We can actually get a nice factor of 15x if we go up to 6 threads in parallel. So why is that? Just very briefly, basically the intuition why we can be so much faster here. So first of all, each of these phases has random access that is relatively local. So it's either within a block of data or it's within a part of data, as we call them. And this local access is always nice because then we can reuse things that are in the so-called CPU caches already. So that really generally speeds up computation quite a bit. In general, also the compactness, like putting such an emphasis on having compact data structures, is also just generally nice for these CPU caches, because again, more things fit into these caches, and then we can access them more quickly if we need to access them multiple times. And so one thing we found surprising while we're building this, we were first imagining that we would build a stiff encoding of the offsets as a last final step. And previous to that, we just used normal like 8-byte integer offsets. But it turned out it was important to have the stiff encoding already, immutable data structure for that already, to then use that while building the hash table. Just having this nice and small made the access so much faster, even though to compute the actual offsets, as I mentioned, we need to do some computations. Anyhow, that's just to give you a bit of intuition of why this is actually faster than the previous approach. Let me now switch gears once more, final time, and tell you a bit about the impact in prod. So first of all, an extreme example, we had a single large hash table in prod that shrunk from 16 gigabytes down to 470 megabytes. So that's a 35x factor, which is pretty extreme. And that was just one important hash table of one customer. For a single customer on the right, you see kind of the workload as it progressed over time. And then at a certain point in time, we switched to the new implementation, the FireHashJoin. And if you look at the red line, which is denoted build time, at the time we switched, it basically dropped by a factor of 9x. So now we're faster by a factor of 9x with respect to the build phase. And if you look at these sort of light green bars in the background, you see that these bars drop by a factor of 5x about. So we use about 5x less RAM just by switching to the new implementation. In total, if we look across all queries in prod, essentially we get a nice factor of 7x speed up for the build phases. So not the entire queries, but the build phases got 7x faster across all queries on all customers in production. Then the TPCH dataset, query set benchmark, we ran that once more. And here end-to-end, so including everything, not just the build phases, this became 2x faster. And finally, this is not prod impact, but this is just a small detail. We also filed a patent for this in mid-23. All right. With that, let me conclude. I hope I was able to convince you that the FireHashJoin is a neat new implementation of the HashJoin algorithm, which gives you an up to 5x smaller memory footprints without compromising on the build time.